Welcome again to the continued class on plastic analysis. So far we have studied in detail the theorems of plastic analysis. Now in order to utilize these theorems, the upper bound theorem and the lower bound theorem, we need to speculate on possible mechanisms. Now here sometimes there may be confusion. All the suggested equations, like the one involving the number of possible mechanisms, they are suggestive in nature. Let's see one example involving higher order of indeterminate structure. Let's say we have the same multi-span beam which we had studied while learning how can we analyze structures of higher order of indeterminacy through the sequential hinge formation, that is the first principles. Now here if we want to use the theorems of plastic analysis for quick solution, then we know that this structure has a degree of indeterminacy of 3. So it suggests that we need 4 hinges to convert the structure into a mechanism, and by using the known relation, the possible number of mechanisms comes out to be 4. So what are those 4 possible mechanisms? One could say that the possible mechanisms are like these. Let's say we create hinges at these supports B, C and D, and then at the point of application of load in the first span, and this gives rise to this particular mechanism. Similarly, we can consider the other spans, and accordingly we'll have these mechanisms. For example, here span BC is undergoing the mechanism formation, and here span CD is undergoing the mechanism formation, and finally we have the rightmost span which undergoes this kind of failure. But then someone can give us an alternate solution also, even with lesser number of hinges. For example, if we consider this kind of mechanism, here just 2 hinges, they are enough to lead to the collapse of the structure. So in the case of the end spans, this kind of mechanism is possible, and in the interior spans we need say 3 hinges to bring about collapse of the structure and the formation of the mechanism like this. So we can have alternate mechanisms also depending on which span we are focusing on. So for the end spans just 2 hinges are enough, and for the interiors we need 3 hinges. So one may get confused that whether these 4 mechanisms are the basic or the independent mechanisms or the other 4. So this shows that all the relations which we derived, they are suggestive in nature. So in general we have some thumb rules. The first thumb rule is that in general simpler mechanisms and those which involve less number of hinges are more likely to be the true mechanism. Secondly, it must also be understood these mechanisms are the independent mechanisms or the basic mechanisms. It is possible that a combination of these mechanisms could be the actual failure mechanism. Let us now consider 2D frames in plastic analysis. In 2D frames, basically the bending moment diagram depends on the loading. The bending moment diagram is important because from the bending moment diagram we determine what are the possible locations of the hinges, and that gives us the count of the total number of possible hinges. For example, if the frame is under a combination of horizontal and vertical loads like this, then there are 5 possible hinge locations as shown here, and if we apply this relation we get 2 independent mechanisms. So these will be the beam and the sway mechanism, as we will learn in the coming slides. On the other hand, when the frame is under only horizontal load, so in this particular scenario we have 4 possible hinge locations. So as a result, calculations show that there is only one possible mechanism and that is the sway mechanism. Now let's see these mechanisms in detail. So essentially, if we have a symmetric frame and the frame is under vertical loads which are also symmetric in nature, so this is a non-sway frame, and typically in this particular configuration it could be very easy to visualize that here only beam mechanism is possible. So beam mechanism means that the plastic hinge formation takes place in the top beam and that is converted into mechanism. So it is like a local failure of a member, and here the columns, they still remain intact, but of course from the point of view of the stability we consider the structure to be failed. Now another situation could be that we have a frame, irrespective of whether it's symmetric or unsymmetric, but it is under horizontal loads. So it is a sway frame, and in this particular situation the possible mechanism is the sway mechanism, where the formation of the hinges takes place in the columns. So here complete collapse of the structure occurs unlike the first mechanism. Besides these two, a third condition is also possible, that possibly if we have a symmetric frame under unsymmetric vertical loading, or we have unsymmetric frame under vertical loading which could be symmetric or unsymmetric. So in both the cases the frame will be a sway frame. So accordingly it can have two possible mechanisms. One is the beam mechanism and the other is the combined mechanism. Now what is combined mechanism? Combined mechanism is basically a mechanism which results from the linear combination of these two mechanisms. So if we just add or superimpose these two mechanisms, we get something like this. But remember that we have not applied here the horizontal load. We are not considering the horizontal load. We are only considering the case that either we have the symmetric frame with unsymmetric vertical loading, or we have unsymmetric frame itself under any kind of loading. So we have a possibility of this kind of combined mechanism. So just see here that this particular hinge will vanish because now there is no net rotation of this particular joint, and we'll see this in detail in the next slide. Now this kind of combined mechanism can also be possible under combination of the horizontal and the vertical loads, that is irrespective of the symmetry or non-symmetry. If the frame is under a combination of horizontal and vertical loads, then also this kind of combined mechanism is possible. Let's study these three mechanisms in detail. So we have first the beam mechanism. So under this mechanism we have the failure of the top beam. So essentially here we use the principle of virtual work. So we apply a small rotation. So when we apply a small rotation, then the net work done has to be computed based on the plastic moments. So the rotation at the midpoint of the beam will be double of that at the ends. So this is the beam mechanism, and in the case of the sway mechanism we have the failure by the development of four hinges in the two columns, both top and bottom. So that leads to the collapse of the entire structure, and here both the columns, they undergo rotation theta when we apply the principle of virtual work. So the rotations etc. which we are showing here, they are corresponding to the virtual displacements which we apply when the structure is just about to fail. Of course the structure would have undergone displacement prior to that, and these small rotations, they are over and above, and they are very infinitesimally small as compared to the main rotations. So this is the sway mechanism. And then for the combined mechanism, if we have, let's say, the combination of the horizontal and vertical loads, and later on we will see that even one of them could cause the combined mechanism. So here this is how the superposition leads to. So the hinge at this particular joint gets cancelled out, because when we give sort of the virtual displacements in the form of rotations, so the two rotations, they cancel out here. So accordingly, now if we find out the net rotations in order to compute the virtual work done, we find that at this particular joint we have 2 theta, because here the beam has undergone rotation theta and the column also has undergone rotation theta, so the net rotation is 2 theta, and at all other joints it's theta. Now let's consider one example. So here we have this frame, unsymmetrical frame. The two columns are of different lengths here, and the frame is under the combined action of horizontal and vertical loads P, and let's say the plastic moment capacity of the section, both beams and columns, is 300 kilonewton meter. So here when we do the calculations we get the answer as 2. So the basic mechanisms or the independent mechanisms are beam and sway, and then we have the combined mechanism. So it is fairly predictive in the case of a single bay, single story frame. The mechanisms could be only 3. So let's find out the failure load for the 3 mechanisms. So for the beam mechanism, this is how the structure would deform, and the external virtual work will be done by the vertical load only and not the horizontal load. So when we write the equation of the external and the internal virtual work done, so we have the external virtual work done by the downward displacement of the vertical load, and then we have the internal virtual work done at these 3 plastic hinge locations, that is at B, C and D. The only difference between these 3 is that the work done at C is twice that of at B and D, for the reasons we have already explained. So solving this equation you will get the value of the failure load as 600 kN. Next we just see the load for the sway mechanism. So for this, if we similarly set up the equations, then we get something like this. So here, so just note that here length is 2 meters and MP is 300 kilonewton meter, and we have the work done at A, B, D and E. So solving we get the answer as 450 kilonewton. And finally, for the case of the combined mechanism, now all the rotations, they are shown here, and now the net rotation here at joint D shall be 3 phi, because the beam undergoes a rotation phi and the column undergoes the rotation 2 phi. So these rotations, as we have clearly explained, they are for the virtual displacements we have awarded to the structure. So here these are the virtual works done internally, and as far as the external virtual work is concerned, both the horizontal and the vertical loads, they will perform virtual works, because this point of application of the horizontal load moves forward and the point of application of the vertical load moves downward. So after solving we will get an answer as 400 kilonewton. So now it should be understood that no work is done at B because of hinge cancellation. Here there is hinge cancellation. What we find is that the lowest load comes for the combined mechanism, but then we must check combined mechanism whether it's true or not. And how do we check? We check by the yield and the equilibrium criteria. Now here if we apply the equilibrium check, that will be a bit difficult, unlike in the case of the beams. In the case of beams we did check on the left part, then on the right part independently, and then we got these reactions independently, and then we checked for the overall equilibrium. Here, as we will see, this approach will be difficult because it will lead to dead end. We will show how this can be circumvented. So what we do, we begin with the column DE, and here we can at the most obtain the horizontal reaction HE here, because otherwise we are not able to obtain both VE and HE together, because we have insufficient number of equations as compared to the unknowns. And after this we can then consider the equilibrium of part CDE, because now we have already VE with us. So from this we can get the vertical reaction at E, and once we have both the horizontal and the vertical reactions, then we can get the remaining unknowns also. these are 300 and minus 300. So minus 300 means that the direction is the opposite of what we have assumed here, so that will be downward. So this is how we have solved for the right part of the structure. Now can we go to solve for the left part? Let's try. So we'll find that it is not possible because we have these two unknowns here and these two unknowns here. Basically we have to consider both the parts independently. Now we cannot make use of what we got from the right part. So left part, what we find that we are at the dead end. So we cannot solve, and even if we try the case of the column as we have done for the right part, we find that this is also of no use. So how do we do? So we abandon this, and instead what we do, we consider the entire structure as a whole. Now we consider the equilibrium of entire structure as a whole. So what we get the values of HA and VA. So far we have used the entire structure and we have also used the right part. Now with this information, let's check the equilibrium of the left part alone. So that's what we are now going to do. So we have the left part now, and this part we can do its equilibrium check. So we do moment equilibrium check about C, and this comes out to be 0. So the equilibrium condition is satisfied. And then we do yield check at B. So for that purpose, we only assume the yield moment at A and keep the moment at B, the internal bending moment, as unknown. And once we apply the equilibrium, we find the bending moment at B to be 100 kN within the limit less than MP. So here the yield condition is satisfied. Similarly, we check for the yield condition at C. So we keep the moment at C unknown. Of course, we know that this is the point of the plastic hinge. So deliberately we are keeping it unknown to get the result from these reactions. And what we find is that this is also satisfied. So this is the true mechanism. So it's your homework that you can check the equilibrium and the yield condition of the other mechanisms. So choose one of the two other mechanisms and do this, and you will find that you will be able to detect that some of these, they are not satisfied. So we have a practice problem for you. So try to do this practice problem and then find out which mechanism is governing and check the mechanism for the satisfaction of the equilibrium and the yield criteria. Now we have learned quite a bit about the frames. So can we eliminate some of the mechanisms under special conditions, maybe under only vertical loads or maybe only under horizontal loads? So let's see if that can be done. So we have two special conditions. So in first case, we have the system that the frame is symmetrical and the frame is under only vertical load, that to applied at the midpoint of the beam. So here we can say with confidence that beam mechanism is definitely possible. Now how about the sway mechanism? Is sway mechanism possible? Yes or no? And then is combined mechanism possible? Yes or no? Can we get the answer? Can we use the virtual work calculations to prove our point? So let's see. So here, if we try to apply sway mechanism on this structure, that is the load undergoes a lateral movement here and not the vertical movement. So when we write the equations for virtual work, we find that there won't be any external virtual work done because there is no displacement under the applied load or in the direction of the applied load. So that part is 0. So this shows that this mechanism is not at all possible. And then how about the combined mechanism? So combined mechanism, if we apply, so here there is movement of the vertical load and it's not just the right ways but also is down. So there is some external virtual work done. So here the equation fits. So here the combined mechanism is theoretically possible, but what our observation says is that the beam mechanism shall be most likely the governing one. And let's consider the sway frame now. So here definitely sway mechanism is possible, And beam mechanism we can prove by using the principle of virtual work is not at all possible, because for beam mechanism the work done will be 0. So this means that the equation between the internal and external virtual work will not have any solution. And how about the combined mechanism? Let's do the check. So here in this particular case, the horizontal force does perform some work. So here the equation fits. So the combined mechanism is also theoretically possible. So in these situations, we have an idea which mechanism is most probable and which mechanism can be possibly eliminated. Now we solve another example. So this example is a bit different. Here we have different moment capacities for the beam and the columns. Beam has double the moment capacity as compared to the column. So this is like a strong beam, weak column structure. Of course, we can have the other option, that is strong column, weak beam. So here for this case, we know that if the joint forms a hinge, then plastification will first occur in the column and not the beam. So that's why this kind of hinge formation is shown like this, that we are showing the hinge in the column portion of the joint and not the beam. So let's first try the beam mechanism. So beam mechanism will be like this. So the hinge formation at the beam column joints will be in the column portion, and at the midpoint of the beam the hinge formation will be like this. So it will involve the beam only. So here the plastic moment capacity is 600 kN and the other hinge locations it's 300 kN. So that difference we have to consider in the calculations. And the rotations are also like this as before, double rotation at the bottom of the beam. So here when we write the equation of equality between the internal and the external virtual works, so what we find is that the two plastic moments we have to take accordingly where the plastic hinge formation takes place. For example, at location C we have to take 600 kN or MP1, and at other locations we have to take 300 kN or MP2, and accordingly the thetas are also different. So we have at B and D we have the rotation phi, and at C it's double. So by doing this calculation we find the value of the failure load as 900 kN. Next we come to the sway mechanism, and here the hinge formation will be like this, again in the columns only, and here at all the 4 locations the plastic moment will be 300 kN, and nowhere we will have 600 kN. So here are the rotations when we apply infinitesimally small virtual displacement in form of rotation. So here we have the angle phi, and here we have 2 phi, and we can set up again the equations of the internal and the external virtual work. So we have all the locations A, B, C and D are using MP2, which is 300 kN, and here the work done by the external force is 2L phi, because 2L is the length of the column and phi is the rotation here. So this net displacement is 2L phi. So solving we get the value as 450 kN, which is lesser than the previous one of 900. Let's now consider the combined mechanism. So here in this particular case we have the hinge cancellation at B, and at other locations we have the plastic moments at D, E and A. The plastic hinge forms at 300 kN, but at C it forms at 600 kN. So we have here the rotations as shown. So for the column we have double the rotation, and for joint D we have 3 times the rotation phi, because here the beam also participates in same amount of rotation, and at the bottom midpoint of the beam we have rotation 2 phi. Now we can write here the equation of the internal and the external virtual work. What you find that at A C, D and E. So among these, at C basically we are using the moment capacity of 600 kN meter, that is MP1, and at all the locations we are using 300 kN meter. And for the external virtual work also, the work is done by both the forces, the horizontal as well as the vertical force. So solving we get a value of 500 kN. So from the analysis of these three cases, we find that the least work is done in the case of the sway mechanism. So sway mechanism is possibly the actual mechanism, but then we must ascertain. And how do we ascertain? By carrying out the equilibrium and the yield check. So it's your homework. You do this equilibrium and yield check and ascertain yourself that the sway mechanism is the correct mechanism. So with this we have finished the case of the normal kind of frames. Now we'll be going to study inclined portal frames from the next class. So thank you very much. We'll meet in our MS Team channel for further discussions and question answers.